Hello students. Today I would like to define what is the concept of connectedness in topological space. Before that, I will introduce what are mutually disjoint and mutually separated sets. Suppose we have a topological space X dot. We have a topological space X dot. Okay, two sets A and B are said to be disjoint, means they have no intersection. They have no common elements. So A and B are disjoint means their intersection is empty or they have no common elements. But which doesn't mean that you can consider its closure. Suppose it is A closure. And suppose this is B closure. Then you can see that there may be common elements for A closure and B closure. Okay. So A and B are mutually disjoint means A intersection B equal to empty, which does not mean A closure intersection B closure, which will be either they may be non-empty. Okay, it is possible. Okay, but we say that two sets A and B are mutually separated. It means, suppose we have a topological space X dot and we have A, B are two sets. Okay. Then you consider its closure. This is some A closure and it is B closure. Then you can see that they have no common elements for A closure and B closure. So I can say that A closure intersection B closure is equal to empty. Since their closure intersection is empty, which always implies A intersection B must be empty. Okay, so which is the definition of mutually separated sets? And this is the definition of mutually disjoint sets. So from the figure, you can say that whenever two sets are mutually separated, then they are clearly mutually disjoint. So I can say that mutually separated sets always implies mutually disjoint. But the converse need not be true because there may be intersection for A closure and B closure. Okay. So now let's define what is the definition of connected set. So the definition says a topological space X dot is said to be connected if it is impossible to find non-empty subsets A and B such that A union B equal to X and A closure intersection B closure is equal to empty. That means the space X is said to be connected mean the whole space X cannot be separated into two non-empty sets A and B. So if we can't write X is equal to A union B where A and B are mutually separated sets, non-empty mutually separated sets, then that space is called connected. Otherwise it is called disconnected. Okay, which is same as in the definition for metric space. Okay, next we have some equivalent statements of connectedness. Let X dot be a topological space. A and B are subsets of X and the following are equivalent. First statement is definition of connectedness. Suppose A union B is equal to capital X and A closure intersection B closure is equal to empty means X can be written union of two separated sets. Therefore, X is disconnected, which means X is disconnected. Then we need to prove these all statements are equivalent. Second one says A union B equal to X and A intersection B equal to empty where A and B are closed in capital X. Okay, and B equal to X minus A and A is open in X. Open means both closed and open. And B equal to X minus A, del A equal to empty. Del A means not del A, dou A equal to empty. Dou A means boundary of A equal to empty. A union B equal to X and A intersection B equal to empty and A and B are open sets in X. Okay, so these are the 5 statements which are equivalent to disconnectedness. Okay, we will prove this. So first we will prove 1 implies 2. 1 implies 2 means assume the First statement, assume A union B equal to capital X, comma, A closure intersection B closure is equal to empty, which means X is disconnected. X is disconnected. We want the second statement. Second statement says A union B equal to X, A intersection B equal to empty, and A and B are closed in X. Okay. Clearly, by the condition given, A union B equal to capital X is here, and A closure intersection B closure equal to empty means A and B are mutually separated. Mutually separated. So you know mutually separated sets are mutually disjoint, which implies A intersection B will be empty. Okay. Then now we want to prove the last one, A and B are closed in X. Claim A comma B are closed in X. So we want to prove A and B are closed sets. Okay. We have A union B equal to capital X. So which implies A union B equal to capital X and A intersection B equal to empty means A is contained in X minus B. Whenever A is contained in X minus B, A closure will be contained in X minus B the whole closure. And we know every set is contained in its closure. So B will be contained in B closure. Since B is contained in B closure means their complement will be reversely contained. So X minus B closure will be contained in X minus B. And here you can say that A closure is contained in X minus B closure actually. Because since A is contained in X minus B and A union B is nothing but capital X, therefore A closure will be contained in X minus B closure also. So here we have X minus B closure is contained in X minus B. Okay. Which implies A closure is contained in X minus B closure and X minus B closure is contained in X minus B, which implies A closure is contained in X minus B. So what is X minus B? You know X minus B contains A, which X minus B is actually is equal to A. So A closure will be contained in A. So we get A closure is contained in A. We all know A will be always contains A closure. So suppose this is equation 1, this is equation 2, then which together implies A closure will be equal to A, which means A is closed. Okay. Similarly, we have A closure intersection B closure is equal to empty, which implies B closure will be contained in its complement. Its complement is X minus A closure. And in a similar way, you can prove that X minus A closure will be contained in X minus A because A is contained in A closure. So their complement X minus A closure will contained in X minus A. Okay. So X minus A closure is contained in X minus A, which implies B closure is contained in, what is X minus A? Since A intersection B equal to empty, we can, and A union B equal to capital X means X minus A is contained in B. So which implies B closure will be contained in what you get now? B closure is contained in X minus A and we have X minus A is contained in B. Therefore, B closure will be contained in X minus A will be contained in B. Together implies B closure is contained in B. B closure is contained in B. And we already have B is contained in B closure. Suppose this is equation A and this is equation B. By A and B, you can have B will be equal to B closure, which implies B is closed in X. So we get the second statement, that is A union B equal to capital X, A intersection B equal to empty, and we have A comma B are closed in X. So this is the second statement. So we proved 1 implies 2. Now we will prove 2 implies 3. So assume the condition 2. 2 means this one. Assume statement 2. What is 3? Statement 3 says that we want to prove we have to prove that B equal to x minus A and A is Klopen in X. A is Klopen in X. This is what we need to prove. Okay, we can assume the second condition, A union B equal to X, A intersection B equal to empty, A and B are closed in X. Okay, so we need only prove that B equal to X minus A first. Since A union B equal to capital X means B will be nothing but X minus A. Okay, union B equal to capital X and B equal to, which means B equal to X minus A. Because A intersection B equal to empty. So which means that suppose this is capital A and this is capital V. We have A intersection B equal to empty and their union equal to capital X. So this is our capital X. The whole shaded region. So you can see that what is B? B equal to X minus A. Its complement is A complement is B, B complement is A. Therefore, B can be written X minus A. Okay. And we need only prove that A is Klopen in X. A is Klopen means A is both closed and open. By assumption, A and B are closed. We have A is closed. Now we prove A is open. We have A is closed and B is closed. Since B is closed, which implies since B is closed, what about its complement? B complement will be open. Or we have B equal to X minus A. So which implies A is closed and instead of B I can write X minus A. X minus A is closed. Whenever X minus A is closed, what will be A? A will be open. Its complement will be open. So which implies A is closed and A is open. Because complement of X minus A is A, since X minus A closed, its complement A will be open. Which implies A is closed and A is open. A is Klopen. So by simple steps, you can prove that 2 implies 3 will be true. So we proved 1 implies 2, 2 implies 3. Now we will prove 3 implies 4. Okay. Now we will prove 3 implies 4. Assume 3. Assume 3 means B equal to X minus A and A is Klopen in X. Klopen in X. We want the fourth statement. Fourth statement is B equal to X minus A and dou A equal to empty. Boundary of A equal to empty set. So we need only prove that boundary of A equal to empty. Okay. And we can assume that A is Klopen in X. A is Klopen implies A is both open and closed. Open and closed. Since A is closed, you can see that since A is closed, A equal to A closure. When a set is closed means the set itself is equal to its closure. Since A is open, we can use the both criteria, closedness and openness. Since A is closed, A equal to A closure. Since A is open, X minus A is closed. Its complement will be closed. Okay. Whenever X minus A is closed, its closure is itself. X minus A whole closure will be equal to X minus A. Okay. Now we want to prove that boundary of A equal to empty. What is boundary of A? By definition, del of A equal to A closure intersection X minus A whole closure. So what is A closure? A closure is A. A intersection. What is X minus A closure? That is X minus A. So A intersection X minus A. Which means A intersection its complement. What is A intersection A complement? Which is always empty. So boundary of A will be equal to empty. Okay. So now we prove 4 implies 5. 4 implies 5. That is, if B equal to X minus A, 4 implies 5. Assume 4. 4 means B equal to X minus A and boundary of A equal to empty. We want to prove A union B equal to capital X, A intersection B equal to empty, and A and B are open in X. Okay. Since B equal to X minus A means its complement is A and A complement will be B. So which means capital X is equal to A union B. Okay. Now what is A intersection B? A intersection B can be written A intersection. Instead of B I can write x minus A. So A intersection x minus A, which is equal to empty. So you can easily get x equal to A union B and A intersection B equal to empty. For the statement 5, A union B equal to x is here, A intersection B equal to empty, also got it. Now we want to prove A and B are open in X. Next we claim that A and B are open in X. Open in capital X. Okay. For that we have boundary of A equal to empty. Boundary of A equal to empty means by definition A closure intersection X minus A whole closure equal to empty. So which implies X minus A whole closure is contained in X minus A closure. Whenever A intersection B equal to empty, A will be contained in complement of B. Okay. So by the same thing, this set will be, second set will be contained in complement of first set. Second set is X minus A whole closure will be contained in complement of first one. A closure, complement of A closure is X minus A closure. So you get X minus A whole closure is contained in X minus A closure. But X minus A closure will be contained in X minus A. Because A is contained in A closure, then its complement will be reversely contained in. So X minus A closure will be always contained in X minus A. So what you get? Which implies X minus A whole closure is contained in X minus A. Okay. So X minus A whole closure is contained in X minus A means you can consider X minus A as a set B. So B closure is contained in B. And already you can know, we know every set is contained in its closure. So considering X minus A as a set, X minus A will be contained in X minus A whole closure. Okay, suppose this is equation 1, this is equation 2. From 1 and 2, X minus A equal to X minus A whole closure, which means X minus A equal to X minus A whole closure means X minus A is closed. X minus A is closed. What is X minus A? B, which implies B is closed. Which implies whenever X minus A is closed, its complement B will be open, right? So A is open. Now we want to prove B is also open. For that, consider boundary of A equal to empty. Boundary of A equal to empty means I can write A closure intersection X minus A whole closure is equal to empty. So which implies A closure is contained in X minus A closure. So which implies, or which is contained in X minus A closure. What will be its complement? It is nothing but X minus A. So you get X minus A. What is this? Which is equal to capital A. So you get A closure will be contained in A. We already know A will be always contained in A closure. We have this. So from this I get A equal to A closure, which implies A is closed. A is closed means what will be its complement? X minus A is open. What is X minus A? X minus A is taken as B, right? X minus A equal to B. B is open. So you get A and B are open. A comma B are open. Both are open. Actually both are open sets. You can prove that it is closed also. But we need only openness. So I take A and B are open. Now we want to prove the last part of the theorem. Phi implies 1. So then only all the statements are equivalent. Okay. So assume the fifth statement, A union B equal to capital X and A intersection B equal to empty, A comma B are open. We want to prove the first statement, that means A union B equal to X, which clearly implies A union B equal to X is here. Okay, then we need to prove A closure intersection B closure is equal to empty. Okay. Since A union B equal to capital X and A intersection B equal to empty means what is B? B will be X minus A. Clearly, B will be X minus A. This is by assumption, okay? By assumption. We have A union B equal to capital X by assumption, which implies B equal to X minus A. Okay. And we have assumed that A and B are open. Since A is open, what about X minus A? X minus A is closed. And we have taken as X minus A as B, which implies B is closed. When B is closed, B closure will be equal to B. Okay. Similarly, since B is open, X minus B is closed. What is X minus B? You can B equal to X minus A, and I can also write A equal to X minus B, okay, from this equation. So X minus B is closed means A is closed, right? A is closed. When A is closed, A closure will be equal to A. Okay. Then what will be A closure intersection B closure? It is nothing but A intersection B. By assumption, we have taken as A intersection B equal to empty. So we get A closure intersection B closure is equal to empty. Which means X is equal to A union B is true and A closure intersection B closure is also empty. That means the first statement is verified, which implies 5 implies 1 is true. So you proved all the statements are equivalent. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and last 5 implies 1 will be true.